Um, one application of a Kalman filter is tracking a vehicle, some other vehicle. That vehicle is going to follow F equals MA, but we don't know the F. We don't know what force. If there's an airplane out there being flown by some pilot, we don't know what the pilot's doing. So how do we track that? Um, so all we know is the second derivative of what we observe um, is basically that force divided by the mass of the thing. So we could do state space. X1 is the position, X2 is the velocity, and derivative of X2 is Y double dot, which is this F, force divided by mass. And you just have a two-state system. This is a continuous time state space model, just two-dimensional. And this sigma sub m is, we really don't know it. It's the variance of this input, but we could take a guess at it. And actually, if you're seeing this, I'm kind of doing this video after I talked about the Singer paper. The Singer paper is all about vehicle tracking. And he has a kind of complicated model to come up with this sigma sub m that involved a mix of discrete and continuous random variables. But anyway, that's some kind of uncertainty on the acceleration or the force that's driving this vehicle. And then we measure just the position, and there's some error on our measurement. And we have gone through how to discretize these continuous time state spaces. We had a way to do that, and here's the results. So here now we have a discrete state space model that is suitable for Kalman filtering. I'm not going to go through this. The R we need for the Kalman filter, which is just a variance of this measurement error. If you want to go one step beyond just treating that unknown input as totally white, you could treat it as as a result of sending white noise through a first order filter. It would look like this. It has this autocorrelation function that looks like this. That kind of, and if you remember, there was a picture of that thing in the Singer paper. I'm doing this after I did a video on the Singer paper, so maybe you're getting things in reverse form. But if you do that, here's now the acceleration. It's more than just white noise. And now we have a three-state variable vector, our state space model. And now we have a different term for that variance. It all came from here. And if you notice, the Singer paper had both these models in it, the 2D model and the 3D model. Once you got to the 3D model, it was a lot more tedious to discretize. And Singer put, especially this Q or this Q matrix, was a whole appendix to the paper, and it was pretty tedious. I don't even write down all the terms. So anyway, this is the result you get after discretizing that three-state example. You go to the limiting cases. This big T here is the time step between samples. How often you get a measurement of position. If it's much smaller than the time constant of the maneuver of the vehicle, this is the limiting case, where it's much smaller. really fast sampling compared to how fast the vehicle could maneuver. And here's the corresponding limiting case for the Q. If that sample time is much larger than the maneuver's time constant, you're back to effectively a two-state state vector. It does you no good to try to estimate the acceleration because you're sampling too slowly, and you're back to modeling it as white noise. So it kind of depends on how fast you sample. I'm not going to go through this, but it's different ways to come up with that Q depending on your model. If you went pure white, you just pick some uncertainty, some variance on that acceleration, on that input. If it's colored, but you have a long sample period, you could justify it based on some variance of the maneuver itself and the time constant of that maneuver. And then if you have a three-state model, you have a way to come up with, well, based on maneuver, variance, and the time constant. Some comments on that Singer paper. I don't want to read every one of these, but Singer did both the two-state model and the three-state model. Saw that, and he did. He assumed a certain probability density function for the target acceleration. That was a thing that was a mix of discrete and continuous. He assumed you had a maximum and minimum, and at certain probabilities, and a probability of no maneuver at all, and uniform in between. And I assigned that to my students as homework. Anyway, that's what Singer did. He showed the autocorrelation function of that target acceleration when it was for the three-state model. It's that first order Gauss-Markov process. He did the standard discretization procedure, which I taught in the previous module in this course. So you can do that now. It was tedious to come up with the Q, especially that 3D Q making in an appendix. He looked at those limiting behaviors where the sampling time was much smaller and then much greater than the maneuvering time constant. I had my students do some of that. For homework. Yeah, here I mentioned this when I was talking about the Singer paper. He has a fairly complex initialization procedure that I wouldn't have done it that way. He needed like 3 measurements to even come up with the first state estimate. Because he used measurements to initialize, where I start. Anyway, and Singer simulated that filter under a spectrum of values, meaning he assumed different these things, sigmas of M and the taus of M, to see how accurate you would track under various assumptions. Anyway, I hope that ends the Singer paper, and I'm still not quite done with the Kalman filter. So I'll save some more for another video.